So this week we're going to be looking at Experiment 9, which is another dry lab. You're going to be working with molecular models. It's very important that you remember to bring your molecular model kit to lab for this laboratory. Being able to work with molecular models is a very important technique that you need to master as you progress in organic chemistry. That's why we're having this laboratory very early on in the semester, even though it is Experiment 9. There's a chart in your lab manual on different types of isomers. And of course, when we're talking about isomers, we're talking about molecules that have the same molecular weight. They have the same formula, basically. So they have the same number of carbons, hydrogens, oxygens, etc. And so when we're talking about the entire class of isomers, we can break that down into two generic types. We can have stereoisomers, which we'll talk about in just a moment, and we can have constitutional isomers. And constitutional isomers are probably the easiest for you to understand. Basically, what we're talking about when we talk about constitutional isomers, just like its name says, we're talking about molecules that have a different constitution. That is, their atoms are connected in a different way. So for example, if you look at pentane, we have 5 carbons, but there's a couple of ways that you can actually connect these 5 carbons, and I'm going to show you 2 right here. We can have what we call N-pentane, where the carbons are lined up in a straight chain, if you will. But we can also have isopentane, where we've moved the connectivity around. So notice now we've only got 4 carbons in a single chain with a methyl group hanging off of it. Has the same molecular formula, same molecular mass as pentane, but nonetheless is a constitutional isomer. We can also have constitutional isomers for other types of molecules that contain functional groups. And when we have constitutional isomers, they contain functional groups. We can actually have 2 different functional groups. So for example, ethanol has a methyl group, a methylene group, and an OH, right? So that's ethanol. But we can move the oxygen in between the 2 carbons, basically, and make dimethyl ether. So we've generated 2 different molecules that have very different physical properties based on the fact that we went from an alcohol functional group to an ether functional group. But nonetheless, these are constitutional isomers of one another. Now, in stereoisomers, we can have 3 different flavors, if you will, of stereoisomers. We've got geometric, configurational, and conformational. We'll talk about each one of these. When we're talking about geometric isomers, we're talking about things like alkenes, for example. And so you can see here, we've got our methyl groups trans to one another. So we have a trans alkene. And in the bottom example, we've got our methyl groups on the same side, or cis to one another. So we have a cis alkene. These molecules have exactly the same name, except one will be called trans-2-butene, the other is called cis-2-butene. So the prefix on the name changes just a little bit, but the parent itself remains the same. We can have configurational isomers, and what we're talking about here are enantiomers, basically. So we have chiral centers, that is carbon atoms with 4 different substituents on them. So here we have R2-chlorobutane, and here we have S2-chlorobutane. They are non-superposable mirror images of one another. And so that we say that they have different configurations. This is the R configuration. This one is drawn as the S configuration. And we can also have conformational isomers where we're talking about alkanes in this particular case. So here we have butane looking down the carbon-2, carbon-3 bond. And you can see the methyl groups are 180 degrees to one another. Recall that the big circle is the carbon behind us. The little dot is the carbon coming towards us. And so these things are connected to the front carbon. Everything that's connected to the big circle is connected to the back carbon. And so we see that these are 180 degrees. This is known as the anti-conformation. But we can rotate around that carbon-carbon single bond, giving rise to a number of different conformations. And when we have these 2 methyl groups closer to one another, as shown here, we have what's known as the gauche conformation. So this is the chart that you need to understand from now on. Basically, you need to know how to identify constitutional isomers, and you need to know how to identify the various stereoisomers that we have, the geometrics, the configurationals, and the conformationals. And what you're going to be doing this week in lab is actually building models of all of these things, and it's actually going to be a discovery process where you learn how to build and use models and discover some things. So let's look at the typical components of the model kit. My model kit's a little different from yours. They contain the same parts basically, except mine came in a nice fancy case. However, yours comes in a plastic bag, but nonetheless you have the same parts. You should have a series of black sp3 hybridized carbon pieces. I'll show you how to put those together in just a moment. You should also have some sp hybridized carbon pieces. This is an alkyne. You can see the triple bond in there. This actually represents two carbons. There's a carbon on this end and a carbon on that end. It's not just one piece. It actually represents two carbons. You should have some sp2 hybridized carbons that look like this. So this is an excellent piece to use for modeling carbocations, etc. And then you're going to have a number of pieces that are actually different colors. Let me go ahead and set this aside for just a second. Show you what we've got here. You should have a number of gray sp2 hybridized carbon pieces. These are excellent for making alkenes and carbonyls. I'll show you how to do that in just a moment. You should have some blue sp3 hybridized pieces. These are usually used to represent nitrogen. And then you have a series of red sp3 hybridized pieces which we use to represent oxygen. And then these light gray pieces are sp3 hybridized carbons, but they're more flexible, so we can bend them. And these are very useful when you're trying to construct strained rings, for example, like cyclopropane. You'll want to use one or two of these pieces to keep from breaking your model kit. It allows ring strain to be modeled quite accurately. Then there's some other colored pieces that we use for a variety of reasons as well. You'll also notice in your kit that you've got some double bond pieces. These are actually used for constructing alkenes from using two of those sp2 hybridized carbons that I just showed you. We'll go through that in just a moment. And you'll also have a number of colored spheres. And these colored spheres come in handy because you can use these to represent large groups that you don't have enough pieces to actually model. So the white spheres typically represent hydrogen. The red spheres typically represent oxygen. And green is usually used for fluorine or chlorine, something like that, and blue for nitrogen. But they can represent just about anything you want. And so you can use those in your modeling process quite easily. So now to make an alkene, you're going to need one of these pieces. And you're going to need a couple of the gray sp2 hybridized pieces. And you simply snap them together. And if you've got a brand new model kit, it can actually be kind of difficult to snap them together the first couple of times. And so there we've got ethylene, basically. So we've got the two carbons connected by a double bond with two places that are with a total of 4 places where we can actually add additional parts of a molecule to without too much trouble. When assembling your sp3 hybridized carbon pieces, make sure that you snap them together well as you can. You want to hear that click. That makes sure that the pieces are actually connected quite securely. And if you don't hear that click, it's probably going to fall apart on you as you continue putting your molecule together. So let's look at a couple of examples here. And let's talk about some configurational isomers. This is from 9.2 in your lab manual. What you can see here is we've got 1, 2, 3, 4 carbons in our carbon chain, and I'm representing the chlorine by a green sphere, and I'm representing the fluorine with a blue sphere. And you can see that this has a 3-dimensional shape to it. The green sphere is coming up towards you. The atom that I'm holding, which is a hydrogen, is going away from you, and then these 4 atoms are lying in the plane of the screen, if you will, that you're watching right now. So if we look at this, we notice that we have a particular configuration at this particular carbon atom because there's 4 different things attached to it. Hydrogen always has the lowest priority. Remember that in assigning stereochemistry using the Kohn-Ingold-Prelog rules or CIP rules that you learned about in class. And of course, chlorine has the highest priority over carbon and hydrogen, so this is number 1. This is going to be number 2. This is going to be number 3, and it looks like it's going in a counterclockwise fashion, and so we have the S configuration at this center. We also have another chiral center here. I'm not going to go through determining its stereochemistry, but just recognize that you can do that quite easily. Now, we can have a diastereomer of this molecule. So we have our molecule here. We put together this other one. And what you notice is, let's see if I can pull that a little better there. These are not the same molecule. It looks the same. We've got a blue sphere on carbon number 3. We've got a green sphere on carbon number 2, and we've got 4 carbons connected together. It looks kind of identical, but notice we can't get everything to line up. Just can't do it. And so we've got a situation here where we've got different molecules. Now, to use your molecules to actually depict Newman projections, this is the back carbon, this is the front carbon, and we're going to draw the anti-conformation of butane. So I've got my front carbon, I've got my back carbon. I need 2 carbons to depict that. And I'm going to use 2 white spheres to represent my 2 methyl groups. So on the back carbon, if I look at it, this should be a methyl group. And of course, we've got the 2 hydrogen coming off to the side. I'm going to rotate my front carbon to get it in the right orientation as depicted on the board, and I'm going to have my other methyl group going 180 degrees to that. So that's what it looks like from a side-on view. Front on, it looks just like the Newman projection, where my back carbon is here, represented by the big circle, my front carbon here being represented by the dot, and again, the white sphere is representing my methyl group. And if you look at this, if you simply took this and smashed this into the board, this is what you would get. And that's really what a Newman projection is looking down a carbon-carbon single bond, putting it in the plane of a board and smashing it into that plane, and what you get from that is a projection of what that looks like. And we can get a number of different projections simply by rotating around that carbon-carbon single bond. So this would represent the Gauss conformation. If everything lines up, this represents an eclipse conformation. And so you're going to be building these models this week in lab. Make sure you read the instruction booklet that came with your model kit. Make sure you review the chapter in your textbook that deals with stereochemistry before coming, and be prepared to spend the entire time building different models, getting comfortable with building models, and answering questions based on model building.